you're going to have to fix it again. So we do not have 365 and 1/4 day calendars. We use a modified one, okay? So we do not use this, we use the Gregorian calendar after the Pope who first fixed it. Here's what we use. We use 365 and 1/4 days asterisk, okay? You may not be aware of the asterisk, but we do not have leap year every 4 years. Occasionally, we will leave one out. It's very occasionally. But the point of occasionally not having a leap year is because if the actual year is 11 minutes short, if occasionally we don't have one, it brings us back kind of to work back up to and sets us back for the round off error. I'll tell you a little bit about the rule of thumb. So someone just came up with this. It's a rule of thumb. It's not perfect. So you look at turn of the century years. Let's put some recent ones, okay? 2000 was the most recent turn of the century. Also happened to be the millennium, but that's neither here nor there. The previous one was 1900. The next one will be 2100. What you do is you check if they're evenly divisible by 400. 1900 is not. 2000 is. 2100 is not. Okay? Now, if it isn't evenly divisible by 400, no leap year that year. That would otherwise be the leap year. Okay? But you don't have one. So there will be stretches of almost 8 years occasionally where we won't have a leap year. Now, 2000 happened to be divisible by 400. So we did have a leap year in 2000. Okay? So the reason why you will probably never notice that we don't have leap year every 4 years is because one of these will never happen in your lifetime. You're going to be, you weren't alive in 1900, you will be dead by 2100, but at the time, I'm sure this will be all over the news, okay? Why aren't we having a leap year this year? And then everyone will know about this, okay? Okay, are there any questions on that? All right, so that's a little bit about the calendar. So that's also the end of the circular motion unit, and let's move forward to the next thing. All right. The next order of business is I've alluded to already. I put this in some of your problem-solving strategies. We've noted that the force approach at this stage is really highly geared towards constant forces and constant acceleration. And I pointed out that if the acceleration isn't constant, we're going to have another method to use. That's what we're going to develop next. That's the work and energy method. So this is the start of the work energy unit. It'll be a very different way of approaching things and in some sense, a very much more powerful method. We couldn't have started here because it is built off the back of forces, okay? So it's taking it one extra level, okay? And it turns out that you can solve an amazingly larger, more complicated problems with relatively little downside, although there is some downside, if you use this strategy. Okay. So let's talk about work. This is a word we use all the time in everyday language. You can actually define it. It's an equation that you can use. And I'm going to try to motivate what that equation is. So let's say I have a mass that's sitting on a table, and I want to push it across the table. Well, pushing a mass around a table seems like a lot of work, okay? So what does that entail exactly? It means pushing on it and allowing it to move. So I'll exert a force and do it over some displacement. And here is my suggested formula for work. I'm going to multiply the amount of force by the amount of displacement. I purposely left the vector hats off of them. These are sizes only. And the reason I've left the vector hats off of it is because while the input here, so the input into this is two vectors, force and displacement, the output, work, is a scalar. It's a number. Which, you know, is how we use it in everyday language, right? You say, man, that was a lot of hard work. You don't say that was a lot of hard work to the left. Okay? It doesn't matter. Okay? You push the box to the right or you push it to the left, it's equally the same amount of work to do that. Okay? So that's why I'm throwing away the vector parts for the moment. I'm just putting in how much each of those vectors is. Let me try to also tell you why I multiplied them. Why did I not divide them, for instance? Well, it's because there's more than one way to do a given amount of work. You could exert a large force over a short displacement or a small force over a large displacement, and there should be some equivalency to the amount of work you've done. So this would be more like a sprint, right? So in a sprint, you exert a lot of force with your legs, but the sprint can be quite short in distance, right? This would be more like a marathon, okay? So a marathon, you're not exactly exerting that much force with your legs at any given time, but you do it over a long distance. And there should be some equivalency to getting the same amount of work done, okay? So it's like the same thing like, you know, if you're doing your homework, right? You can work really hard for a short time, or you can work more lazy but do it over a longer period of time or something like that, okay? So there should be some equivalency. That's why I multiplied these two quantities. Now this formula is actually pretty much correct for the situation I've drawn. It has a few bells and whistles missing. But those bells and whistles, which I'll get to in just a second, do not affect the units. So this is already a good time to discuss the units of work. The units of work will be the units of force times the units of displacement. And in SI units, what do we measure force in? Newtons. And how about displacement? Meters. So the units of work are Newton meters. That gets its own abbreviation. It's called a joule, capital J. So 1 joule of work is the amount of work you do when you exert a 1 Newton force over a 1 meter distance. Okay? 1 meter displacement. I guess I should remind you that a Newton itself was an abbreviation. So Newton was a kilogram meter per second squared. Force times it's mass times acceleration, right? So this is just throwing in an extra meter. So kilogram meter squared per second squared. That's what a joule is. It's a composite unit. It's an abbreviation for kilogram meters squared per second squared. So I think that's our second composite unit. Composite meaning that it's made out of those fundamental units we introduced on the first day of class, kilograms, meters, seconds, and radians. All right. So, are there any questions so far? Yeah?
Is it anything to do with chemistry, joules?
Same joule.
Same joule?
Yep, absolutely.
Cool.
So
I'm
we'll,
just trying to make the same name for different things again.
yeah, I'll get into the joules that you have in chemistry, or you might use calories, which is another unit, right?
Mm-hmm.
There's an equivalence between calories and joules. So it's just a conversion factor, just like between meters and centimeters, just the thing. All right, so the question then just becomes, what, if anything, do I need to do to modify this to make it fully general? Now, one of the interesting things that is implied by this formula is if you don't displace something, then the work will be 0. That seems to run directly afoul of everyday intuition, okay? So, to give you an example, if I sit there and I push on this wall, if I push on this wall all day, I might say that's a lot of hard work to sit there and push on a wall all day. But since there's no displacement, I'm not displacing the wall, right? Then there's no work done on the wall. So that seems like there's something wrong, right? Now, I can't quite yet explain to you why those are not contradictions. But I guess the hint that I'll give you is that something is being displaced, even if you push on a wall all day. I just don't want to tell you yet what exactly that is, okay? But for right now, we're going to have to accept the fact that when there's no displacement, there's no work. So we'll come back to later why this is and why this makes sense. But that means that I'm going to have to make a modification to my work just a little bit. So let's suppose that I'm pushing that same box along the table, but I do it at a diagonal angle like this. Now you might ask, well, if you exert a diagonal force like that, how can it move in a different direction? Well, obviously there are other forces involved besides just my pushing force. There may be normal force, gravity, friction, all those things. That still doesn't negate the question about how much work does this force do, okay? Now what I want to do is I want to split up the force into two components, F parallel and F perpendicular. And I don't mean to the surface, I mean relative to the displacement, okay? So these are relative to the displacement vector. So any force in general can be thought of as having a component that is along the same line as the motion, and then another component which may be present is force that is perpendicular. And this is my opportunity to point out to you that F perpendicular, if that's all there was, this thing wouldn't even move, right? So F perpendicular is not at all responsible for this motion. In fact, I can say that this component does no work. The reason why this is displacing is entirely due to the parallel component. So we find that really it's only the parallel component that can actually do any work. That right there is the formula that fully encapsulates a general situation. If I go over here, of course I realized, why was my initial guess correct? It was correct because here my entire force happened to be parallel, right? There was no part that was perpendicular. So that was a perfectly fine statement to say that there the entire force did work, but in general, if there's a component of the force that's not along the line of displacement, it does no work, and the only part that it matters is the parallel part, okay? So this is now my general formula, okay? This is my general case. There's nothing really left to be desired there. There's nothing missing. However, I want to get it into a more user-friendly form. I want to get it into a form that just set it and forget it, don't have to worry about anything. And the first thing I'm going to do is do the SOHCAHTOA once so I never have to do it again. Okay? So I pick this theta, and then F parallel is F cos theta. So you can and should be skeptical if you ever try to do a SOHCAHTOA once and for all, so you never have to do it again. You can, of course, at this point know that one person's cosine is another person's sine, right? So couldn't you break it up like this? First this way, then this way. This angle would be phi, right? And the component I'd be interested in, the parallel part, would be F sine phi. So where do I get off calling it F cosine theta when it could be F sine phi? Well, here's how. Anytime someone tries to work some trig function like cosine or sine into a formula permanently, you had better bet that there is some very specific way of picking the angle so that it's the correct angle. So it's going to be cosine if I pick phi correctly, or sorry, if I pick theta correctly. So how do I pick theta and note by mistake get phi? Here's how. Theta is a special angle, phi is not. What's special about it? This is what's special about it. If you take your displacement vector and your force vector and you put them tail to tail like this, the angle between them is not phi, it's theta. Hopefully you can see the geometry of that, right? If I take these two arrows like this and I put them tail to tail, the angle between them will be the angle I've identified as theta, not phi. What is theta? Theta is the angle between the two vectors. I write it like this. Now, when we talk about the angle between two vectors, that's a very specific thing you have to do when you talk about the angle between them. You have to place them tail to tail, okay? You place them tail to tail, and you measure the shortest angle between them, which will range from a minimum of 0 if they're pointed the same way, and the biggest it can be is 180. Okay, so we're talking about the angle between two vectors. They're tail to tail. It can be 0 if they're pointed the same way. It can grow. It can be 90. It can even be as big as 180, but it can't be bigger than that, because if you make it bigger than that, well, remember, if you measure the shortest way, it's closing again, right? So the most they can be is 180 degrees apart. It's also, when you're doing it tail to tail, don't mix this up with head to tail. Head to tail is for vector addition. We're not adding these vectors. In fact, I should point out these vectors aren't even addable. You can add a force to a force or displacement to a displacement. You can't add displacement to a force. That's like adding a meter to a second. It has no meaning. We're not adding these vectors. These vectors aren't even addable. We're discussing the angle between them. And that angle is theta. So to finally clean this up, all these parentheses are a bit silly because these are all multiplied. We have f times delta x times cosine of theta. And the formula, cosine is the permanent thing. It's always cosine. You never have to worry about if it's cosine or sine. It's always cosine. But you have to pick this angle correctly. It's the angle between the force and displacement vectors when they're placed tail to tail. It ranges from a minimum of 0 to a maximum of 180. And that right there is our final, meant for ease of user interface, work formula. We've done the SOHCAHTOA once, so we never have to do it again. That's what we're trying to get away from. So we work in cosine in there on a permanent basis with the angle having to be picked in this particular way. Now, we said that these are just the sizes only of these vectors. They're always positive. However, we get an interesting complication that arises because of our new term. Our new term, again, remember what that's for? It's to acknowledge the fact that not all of the force may be along the same line as the displacement. If this angle has a range of 0 to 180, cosine can actually be negative in that range. So it is possible for this value to be positive, 0, or negative. Let me draw these cases in. Here are my cases. It could look like this, with the angle being between 0 and 90. So that this is when the force and displacement are more in the same direction, the same general direction. Then the cosine of theta is positive, and the work will be positive. Because whatever the cosine does controls whether the work itself comes out to be plus 0 minus. This is when they're more in the same direction. You could have that the force and displacement are perpendicular. That's when theta is 90. What's cosine of 90?
0.
I heard it over there.
0.
0, yeah. That's going to zero out the whole work. Now that's actually not surprising, right? Because that force has no part along that line that displacement is on, right? So we said that was the whole component we were going to throw away, and that's all that force has, right? But then we get into, what if the angle between them is more than 90? What if it's between 90 and 180? That's when the force is more against the motion. What's cosine of a number between 90 and 180 degrees? That's going to be negative. And that's going to control the fact that the work is negative. So this cosine term is going to control the sign of the work. So the question then becomes, well, what does that mean? That the work is positive, 0, or negative? Because we just got through saying it's a scalar. It's a number. It's not a vector. So what does negative then mean? Well, this is when I remind you that you probably knew what a negative number was far before you know that negative could be represented as to the left, right? So if you have a negative balance on your bank account, it does not mean you have, $5 to the left, okay? There's a meaning to signs that has nothing to do with direction. It was a convenient use of plus and minus to indicate direction for vector quantities on a single axis, but doesn't have to be that. So the question is then, what is the meaning? What is the meaning of this sign, of these signs, because it's not direction? So that analogy of the bank account, this idea of having a positive or negative balance, it has nothing to do with direction. It has to do with a surplus or a debt. It's going to turn out that that's exactly what is going on here. So I'm not going to get to that today. I'll talk about this more next time.